Okay. So the next topic is design of compression members. Obviously, we are doing IS 456 2000. So the same, that is by limited methods of design. Now, first question is, what is compression member? A compression member is a structural element which is subjected to axial compressive force. Basically, where we see that the compressive force is encountered, those members are called compression members. Most commonly used compression members are column in the building. Okay, all of us see this. Okay, in building, every building there are some type of columns. Now, Cookbook has defined what is column. Generally, if we say a compression member, we understand that column, but there are some divisions are there. There are something called column and something also called that pedestal. Now, what is a column? Cookbook has defined what is column. A column is a compression member whose effective length exceeds 3 times the least lateral dimensions. Okay, say for example, if I say this is a column, so this is one column, some longitudinal column. Okay, just for example, don't take it a perfect one. Say this is the effective length. Okay, if I take the section, say this is the section of the column, is talking about the least lateral dimension. Say this one, I am talking about, say this one, just I have written a D. Then it is said that it will be said as a column if this is greater than 3d1. If it is not greater than 3d1, then it is called pedestal, whose effective length is less than 3 times the least lateral dimension is called pedestal. So, if it is this one, then it is called column. Okay. If L effective is less than 3d1, then it is called pedestal, P-E-D-E-S-T-A-L. Remember it, this is called pedestals. Okay. Anyway, so our target is to design the compression members. So, before I go for design of compression member, there are various classifications of compression member, and it depends on the various factors. One classification is based on the reinforcement. So, first classification, what we said, that the classification of column based on reinforcement. Based on the reinforcement, column is actually classified into 3 different groups. First one is called tied column. First one is called tied column. Then second one is called spiral column, tied column, spiral column, and the third one is composite column. Composite column. Okay. Now, we will see one by one. I am not going much details. I will just draw the figures and try to show you how it is tied column. Suppose we have a rectangular column. Okay. So, this column will no doubt will have at least 4 reinforcement, longitudinal reinforcement in the 4 corner, and that will have a transverse reinforcement. Okay. That is horizontal reinforcements like that. Now, if I draw this column in the section, longitudinal section, say this is the column, this column will have longitudinal reinforcements. I am showing by the red color as longitudinal reinforcement. Okay, and then it will have transverse reinforcement, that I am showing by green color. Okay, so these are the transverse reinforcement. Okay, simply what I can say, that in case of transverse reinforcement, single ring are made in a layman language. If I say that, so okay, this type of ring are made and joined with the vertical columns. Okay, then this type of columns are called tied column. Then what is spiral column? In spiral column, actually is reinforcements are not provided like that. In spiral column, reinforcements are provided in a different way. Say I am just showing this. Say these are the vertical reinforcement. Okay, and then the spiral reinforcements are provided like that. So, this is how a spring shape, you can say, in a general language you can say a spring shape. Continuously the reinforcement will be provided like that. So, if you see the section will be almost similar. But this is done, in which case this is done for a circular column. Say we have a circular column like that. Then circular column generally minimum 6 reinforcement, particle reinforcement are provided. So if you see the section, you will not understand this part, but in longitudinal section you will understand that a spring, basically a spring like that system reinforcements are provided. So these are called spiral column. Third one is the composite column. Composite column is basically where we provide the steel girder or steel I section. Okay, in addition to the maybe reinforcement may be there or may not be there. Okay, say in that case I am providing a steel girder here, and in addition to that I am providing 4 vertical reinforcement at the 4 corner, and then I can provide spiral reinforcement also to join them, this vertical reinforcements like that. Okay, it should be inside. So this type of systems are called composite column. So what we can see that the column can be classified into 3 classes based on the reinforcement, that is tied column, spiral column and composite column. Okay, now we'll see the next classification. Now this column is also classified based on the loading. Okay, so number 2 category of classification based on loading. Let us see how the columns are classified based on loading. I will write first and then I will show in figures. So number A is called column with axial loading or axially loaded column, we can say sometimes. Column with axial loading, or you can say axially loaded column. Axially loaded column. Number B category is column with uniaxial eccentric loading. Column with uniaxial eccentric loading, or we can say uniaxially loaded column. Uniaxially, check the spelling, loaded, or uniaxially eccentric column, or uniaxially loaded eccentric column, whatever the way you want to say. And the third category is column with biaxial eccentric loading. Column with biaxial eccentric loading, or we can say biaxially loaded column. Now let us see one by one how they looks, or what is the loading where we can say that it is a uniaxial. Suppose I have a column, this is a column, and on that column, say this is the x axis and y axis, and the load is exactly at the CG in both the direction, wherever the CG location, load is exactly applied on that CG. Then we can say it is a axially loaded column. Okay, so this is the column. Okay, and this is the CG of the column, and load is exactly at the CG of the column. Then we can call it as axially loaded column. Okay, next one is the uniaxially loaded column. Say this is the column. Okay, so this column will have either, this is the x axis and y axis. Now the load may be either on x axis or it may be on y axis. Say if it is in this their x axis, or it may happen it may be on y axis. Okay, in any one axis the load will be, then that is called uniaxially loaded column, or loading with uniaxial extension. Even it can be outside also. Okay, AR also it can be. Okay, but it is any one of the axis, or in this axis or in this axis. Okay, so if I want to find out the moment, say load is in this particular location, if this is eccentricity, then what is the moment, if this is P, so moment will be M into E. Okay, so this is called second category, that is uniaxially loaded column. Now third category, in third category load may be anywhere, okay, except those CG line. So these are the CG line. So anywhere it can be here, it can be here, anywhere it can be, load can be anywhere. Then these are called biaxially loaded column, or loading with biaxial eccentricities. Okay, in that case movement in x direction as well as movement in y direction both will come. Suppose if the load is in this location, so I have to know this distance, I have to know this distance. So this is a, if you say Ex, this if you say Ey, then both directions we have to calculate the movements, and then we have to do the analysis parts. Okay, so this is the third category, another category that is based on the loading. Next part, classification of column based on the slenderness ratio. Okay, so third category is based on slenderness ratio. So before I say what is the classification details, we need to know what is slenderness ratio. Okay, write down what is slenderness ratio. A slenderness ratio is a geometrical property of a compression member which is related to the ratio of its effective length to its lateral dimension. Slenderness ratio is basically called the effective length to the lateral dimension. Okay, it may be in x or it may be in dy. Okay, any lateral dimension. So okay, let us say it is d. Okay, in any direction it can be. So I can say that this is divided by d. Okay, that is effective length. It is the ratio of effective length to the lateral dimension. Lateral dimensions. Okay, in any direction it can be. Okay, now based on this we can differentiate the column into two categories. One is called short column, and another is called long column. Now IS 450 Cookbook has defined that when L effective by D in both direction, there is L effective in x direction divided by dx and L effective in y direction divided by dy, both are less than or equal to 12, then it is called short column. Okay, both direction it should be less than 12, then we can call it as a short column. Otherwise it will be called as a long column, not less than equal to less than 12. Okay, if both direction if it is less than 12, then we can say it is. So on the other side, if it is any one of them is not less than 12, then we will be called as a long column. Okay, so this is how we can again define the column in short column and long column. Long column generally fails on buckling and short column fails on crushing. Okay, so this is the another classification. So what we can see that there are three types of classifications are there. Now in this case I have used a term here, that is effective length. Okay, dimensions we understand that suppose I have a column like that, then what is the dimensions in this direction or what is the dimension in this direction, that is called dx or dy. Or if I have a circular column, then everything it will be diameter will be d. Okay, so no issue, circular column it is one side. Now question is what is this effective length. Okay, so let us see what is the effective length. Basically the effective length of a column frame is defined as the length of hinged ended column whose elastic critical load is the same as the theoretical critical load of the framed member under consideration. Okay, or in otherwise, if we do not understand this technical term, if we do not understand, then in a simple way I will show you what is effective length. Okay, so whenever we design, we need this effective length. So this effective length is basically is equal to a constant k into length L. This length L is called the unsupported length and this k is called the effective length ratio. So we need to find out what is the effective length ratio. This effective length ratio depends on the support condition. An unsupported length is basically the clear distance between the floor and the shallower beam frame into the column. Basically what it is saying that suppose if you have a floor, this one, and this is another floor, and in this floor suppose you have a beam like that. So from this beam point to the floor point, what is this height? This height is called the unsupported length, not from up to this, up to the beam point. Okay, and this K is called the effective length ratio, and this length ratio depend on the support conditions. Okay, before I go to the support conditions, there are support condition, or we can say the boundary conditions. So based on the boundary conditions, the column, again this effective columns are classified into two classes. One is called braced against sideway, another is called unbraced against sideway. Okay, that means what I am trying to say that when the relative transverse displacement between the upper and lower ends of a column is prevented, again I am saying the relative transverse displacement of the upper and lower ends of a column is prevented, then the frame is said to be braced against sideway. On the other end, what we can say about unbraced against sideway? When the relative transverse displacement between the upper and lower end of a column is not prevented, the frame is said to be unbraced against sideway. Okay, I will give you the example for column braced against sideway. When both ends fixed rotationally, suppose I am saying here this column, if you take, and this part you take, both ends are fixed rotationally. Okay, both ends fixed rotationally. Now what is the definition? I said braced. I said when the relative transverse displacement between the upper and lower ends of the column is prevented. Okay, you see here now it cannot even move horizontally, not this direction also, not this direction also. Here also it cannot move, so relative displacement is prevented. Okay, then it is called braced against sideway. Braced against sideway. Okay, now take another example. Okay, so both ends fixed rotationally, both end fixed rotationally, or both end fixed and other partially fixed, something like if I say that this type of systems. Okay, and say this is a column. Now you see what I can do, I can block vertical movement. Okay, but in this case, in this end, horizontal movements is permitted. So what I am saying that both end fixed, but the other partially fixed. This is partially fixed and partially movement is permitted. So this type of case it is called unbraced against sideway. Okay, so depending on the different support conditions, we can know what will be the value of effective length ratio. But in general, when it is braced against sideway, the effective length ratio varies from 0.5 to 1, and when it is unbraced against sideway, effective length ratio is more than 1. Okay, varies between 1 to infinity, you can say, when it is unbraced against sideway, and when it is braced against sideway, it is 0.5 to 1. Okay, now we will see the codebook guidelines, what is given in the codebook, rather than this more explanation. Okay, if you see the codebook, this is a copy of the codebook that I have brought for you. If you see here, the degree of end restriction of compression member here symbol is given and theoretical value of the effective length and recommended value of the effective. We will be using the recommended value of the effective length. So first one, effectively held in position and restrained against rotation in both ends. So it is held in position and rotation both are blocked. Theoretical value is 0.5 L, but recommended value is 0.65 L. So we will be using 0.65 L. Okay, effectively held in position at both ends, restrained against rotation at one end. This one end horizontal movement is permitted. Here it is not permitted. So these are basically braced against sideway. Okay, this value is 0.8 L. Effectively held in position at both ends but not restrained against rotation. Here it is not permitted. So effective length is 1 L. This is also coming under braced against sideway. So first three category here it is coming braced against sideway. Okay, here you can see the effective length is up to 1 L. Now come to the other categories. There are other many categories are there which seldomly we need for our purpose. Okay, what is that? Effectively held in position and restrained against rotation at one end and at the other restrained against rotation but not held in position. So in this case restrained against rotation, restrained against position at both ends but one end is not restrained, free. So in this case theoretically 1 L but IRC recommended value is 1.2 L. So from this onwards actually demarcation line is there. This you can say demarcation line. This part is unbraced against sideway, bottom onward. Okay, so this side onwards it is unbraced against sideway, unbraced. Okay, and the upper part is braced. Then effectively held in position and restrained against rotation in one end and at the other end partially restrained against rotation. See, all these cases these values are coming more than 1. Okay, 1 it can go up to infinity. So when we can say these values are more than 1 and can go up to infinity, these are called unbraced against sideway and these are called braced against sideway. So for our design purpose, for our calculation purpose, we need to know this value. Okay, some cases without knowing this value, but just to know that if it is a braced or unbraced, still we can solve some problems. Okay, but many of the problems we need to know this value. So try to remember this value, or if you have wherever in a competitive exam you may not have the access of the code book, so you need to remember that for the class exam points of view, anywhere you can use this value, you can use the code book. Okay, so try to remember these values. Okay, these values are important for the design purpose. Okay, now we will go to the code book and we will see what are the different guidelines given in the code book for design of a compression members. So basically we can say that codal recommendation, or we can say it as a called as a code recommendation. Okay, so we will discuss the code recommendation for compression member recommendation. Okay, first of all the code is recommended regarding slenderness limit, okay, this is given in clause slenderness limit is given in clause number 25.3, clause number 25.3. okay, under that if you go clause number 25.3.1, clause number 25.3 number 1, this is available in page number 46. What it is said that the unsupported length between end restraint shall not exceed 60 times the least lateral dimension of a column. So it's saying that the unsupported length between end restraints shall not exceed 60 times the least lateral dimension, or in other word we can say it is saying L by D should be less than or equal to 60. Okay, so what is this L? Where L is the length, okay, and basically the length, unsupported length we is talking about, and D is the least lateral dimension. Suppose if we have a rectangular column, then out of these two whichever is minimum, say this is D, or if we have a circular column, then this is D. Okay, so this is one condition. Then the other condition said in this under this is that if in any given plane one end of a column is unrestrained, basically talking about the cantilever column, its unsupported length L shall not exceed 100 b square divided by d. Okay, basically in case of column, this L shall not exceed this, or other way we can write shall be less than or equal to 100 b square divided by d. Okay, what is that b and d? Here d is the depth of the cross section measured in the plane of the cantilever, and b is the width, that is the perpendicular other direction. Okay, b is the other direction and d is the measured along the plane of the cantilever. Okay, basically the dimensions of the column it is talking about. Okay, so this is the first codal provision we need to refer, 25.3.1, that these two provisions must satisfy. Okay, now come to the next one. Next one is given about minimum eccentricity. Minimum eccentricities. Sometimes what happen, even we try to design it as a axially loaded column, but still some reasons the load may be little bit here and there. Okay, then codebook has given a provision that if the eccentricity is within that limit, then still we can accept this as a axially loaded column. So what is this? This is available in clause number 25.4. I will read this sentence given in the codebook, then I will write it. All columns shall be designed for minimum eccentricity equal to the unsupported length of column divided by 500 plus lateral dimension by 30, subjected to a minimum of 20 mm. Okay, so what it is saying that the minimum eccentricity, this Ex, suppose in x direction, it should be L by 500 plus dx by 30, if I say in this direction, that is x direction, or 20 mm. Okay, whichever is larger. Eccentricity in x, again I am reading, a column shall be designed for a minimum eccentricity equal to the unsupported length of column divided by 500 plus lateral dimension of by 30, subject to a minimum of 20 mm. So out of these two, whichever will be the larger, that will be called the eccentricity, minimum eccentricity, basically Ex, minimum eccentricity in x direction. Similarly, minimum eccentricity in y direction will be equal to L by 500 plus dy by 30 or 20 mm, whichever is larger. Okay, that should be the minimum eccentricity. For non-rectangular section and non-circular, for non-rectangular and non-circular section, this E minimum is to be taken as L effective by 300 or 20 mm, whichever is larger. This is for non-rectangular and non-circular, non-rectangular and non-circular. Okay. For circular case, it is same as that earlier whatever I said. It will be L by 500 plus D by 30 or 20 mm, whichever is larger. Okay. Here L indicating the effective length. First one, this is here L is the unsupported length. Okay, is said unsupported length L. Okay, but in this case this L is indicating the effective length here. Okay, so LE is basically effective length, but if simple L wherever I have written, that indicating the unsupported length, that is original length of the column. So this was the guideline for minimum eccentricity. Okay, next we will see the guidelines for requirements of reinforcements and their detailing. Okay, what are the different guidelines given in the code book to provide the reinforcements. Okay, So you can give a heading, requirements on reinforcement and detailing. Requirements on reinforcement and its detailing. Okay. First we will see the longitudinal reinforcement. Okay, how to provide the longitudinal reinforcement. Cookbook said that minimum longitudinal bars have a cross sectional area not less than 0.8% of the gross area of the column section. Okay, what it is saying that the minimum reinforcement should not be less than 0.8% of the gross cross sectional area of the column. Okay, so gross cross sectional area of the column, that means whatever the B and D is given, find out the gross cross sectional area, and this value should not be less than 0.8%. that is the minimum reinforcements. Okay, however, in case of pedestal, generally in pedestals are plain concrete column, still in that case also we have to provide a minimum of 0.15% of the gross cross sectional area. Okay, then again it said about in case of reinforced concrete wall, because that is also a compression members. In case of reinforced concrete wall, we should provide a minimum reinforcement of 0.15% of the gross area. Okay, so 0.15% of the gross area, and in case of this what is called deformed bars, this value may be reduced to 0.12%. Okay, so these are the various guidelines that is given in the code book for longitudinal minimum requirements of the longitudinal reinforcement. Again, what it is saying that wherever we are using this deformed bars, that is Fe415 steel with a minimum reinforcement of 0.12%, in that case we should provide a diameter of main reinforcement, a maximum diameter of the main reinforcement of 16 mm, and the reinforcement should be provided in 2 layers. Okay, so this is the condition of the minimum reinforcements. Okay, mainly for the column it should be minimum of 0.8% of the gross cross sectional area. Okay, now next we will see the maximum reinforcement. So next you write down maximum reinforcements. Okay, maximum reinforcement. So as per the code book, it is saying that the maximum reinforcement shall not exceed 4% of the gross area of the column. However, it may be reduced to 4%. Okay, that means in any case that the maximum reinforcement shall not exceed 4% of the gross cross sectional area of the column. Okay, so this is the amount we are talking about. Next we will see the diameter. What should be the minimum diameter and number of bars and their locations. Okay, so that is also given in the code book. It is said that the longitudinal bars in the column, you can give a heading, minimum dia, then number of bars and their locations. Okay, code book is saying that the longitudinal bars should not be less than 12 mm dia. Okay, longitudinal bars should not be less than 12 mm dia, and it should not be spaced more than 300 mm apart. That means it is showing that center to center spacing should not be more than 300 mm along the periphery of the column. Okay, along the periphery of the column, its spacing shall not be more than 300 mm. Next, what it is saying that at least 4 bars, one each at each corner, shall be provided in case of rectangular or square column. In case of circular column, at least 6 bars equally spaced along the near the periphery shall be provided. Okay, so this is the minimum guidelines that we have to follow. In spiral column, the longitudinal bars should be placed in contact with the spiral reinforcement. Okay, in case of spiral spiral bars, the spiral bars should be closely contact with the longitudinal reinforcement. Okay, and longitudinal bars are usually provided close to the periphery. When large number of bars are needed, they may be bundled. Or may be alternatively grouped. Okay, so this is how the longitudinal bars are to be provided. Next part is the clear cover of the reinforcement. It is recommended that a minimum clear cover of 40 mm or bar diameter, minimum clear cover of 40 mm or bar diameter, whichever is greater, is to be provided. Okay, whichever is greater is to be provided. However, some exceptions are there. When the least lateral dimension is less than 200 mm, whose reinforcement do not exceed 12 mm, in that case a clear cover of 25 mm is accepted. Again I am saying, when the least lateral dimension is less than or equal to 200 mm, whose main reinforcements are not more than 12 mm, in that case a clear cover of 25 mm is accepted. In case of walls, a clear cover of 15 mm is accepted. Okay. However, in case of aggressive environment, it is desirable to be provided a higher clear cover of up to 75 mm. Okay. So this is the guidelines how the reinforcements are to be provided. Basically the longitudinal reinforcement, their diameter, their clear cover, etc. Okay. Next we will see the transverse reinforcement. So this provision is given in clause number 26.5.3.2. So we will see the next part is the transverse reinforcement. Clause number 26.5.3.2. Okay, you will open the code book and see in clause number 26.5.3.2 what is written there. This is very difficult to write. Okay, so clause number 26.5.3.2 has given a details on transverse reinforcements and their arrangements. Okay. So first of all, why to provide transverse reinforcement? The reason is that it is provided to prevent the premature buckling of individual main reinforcement. It is provided to confine the concrete in the core area. It is provided to hold the longitudinal bars in position during the construction, and also it is provided to create resistance against shear and torsion. Okay, we have seen earlier cases also in case of beam and all those things. Okay, so these are some purpose for which we have to provide. Okay, now there are two types of spiral reinforcement we have discussed earlier. One is the lateral ties that we have discussed, and another is the spiral reinforcement. Lateral ties are provided, see we have seen there are three types of, that is tied column. So in case of tied column we provide the lateral ties. Okay, so first is basically lateral ties. When we provide lateral ties, in case of tied column. Okay, lateral ties guideline is saying that the tie diameter, okay, I'll go to the next page. Tie diameter, it is generally denoted by phi t, must be greater than or equal to phi long max by 4 or 6 mm, whichever is higher, and tie spacing, that is denoted by st, must be less than or equal to d, then 16 phi long minimum or 300 mm. What is saying here? Tie diameter, that's lateral ties whatever we are using, the diameter of this lateral ties, okay, should be greater than phi long max, means longitudinal bars. Sometimes we are providing defined diameter of the longitudinal bar, so it is talking about the maximum diameter of the longitudinal bars divided by 4 or 6 mm, whichever is greater. So we have to choose the spacing in such a way that it should be greater than out of these two. Suppose your main reinforcement is 25 mm, so 25 by 4 is say how much, 6.25, and this 6 mm, so which one is larger, 6.25. so we have to provide a reinforcement which is more than 6.25. more than 6.25, what diameter is available, that is 8 mm. so in that case we are going to provide a 8 mm dia bar. Okay, next spacing. Set D is the dimension. Suppose we have a dimensions like that, suppose out of these two which one is minimum, say this is 450, 16 phi long minimum. So minimum diameter, say we have 20 and 25 diameter longitudinal bars we have used, so which one is minimum, 20 is the minimum, so 16 time of this is how much, 320 or 300 mm. So 450, 320, 300, out of this which one is minimum, minimum is 300, so our spacing should be less than 300 mm. Okay, that's what it is saying, how to provide the spacing. Okay, spacing of the transverse reinforcement. So this is in case of tied column. Next we will see in case of the other one, that is in case of spiral column. Okay, how to provide the reinforcements. So in case of spiral, or sometimes it is also called helical. Okay, some books you will find that is written, or in food book also, helical reinforcement or spiral reinforcement. How to provide this is what is the spiral reinforcement, right? So this center to center is called pitch. This center to center distance is called pitch. Good book is given a guideline that is saying that this pitch ST, this pitch ST must be less than 75 mm or core diameter of the column divided by 6. I will tell you what is core diameter of the column. It is saying that its pitch must be less than 75 or core diameter of the column by 6, and the pitch STB must be greater than 25 mm or 3 phi t. This phi t is the diameter of the spiral or helical. The diameter of the spiral or the helical reinforcement is same as the diameter of the tie dia, whatever we said, same way you can calculate it. Once we calculate it, then we will calculate the spacing. 75 mm or core diameter by 6. Here core dia means, suppose we have, this is the column and then we have provided the reinforcement cell like that. Okay, So deduct this clear cover this side, then whatever be the dia left after deducting the clear cover, that diameter is called core dia. Okay, so core diameter by 6 or 75 mm. Out of this, whichever is lower, okay, whichever is least, the spacing must be less than that. Fine. Second, spacing must be greater than 25 mm or 350. Suppose you are using 8 mm dia spiral bar diameter, then 350 means 3 into 8 24 or 25. So it must be greater than, so it should be larger. Okay. Out of this, which one is larger? So 25 से ज़्यादा होना चाहिए. So this is how we can decide what should be the spacing and what should be the pitch. Now, Cookbook has given some other conditions of how to find out the reinforcement in case of spiral and all. These are basically whatever I said is the general conditions for any kind of column design. Okay, that means it may be a long column, it may be a short column, or suppose helical reinforcement, all those things. Now we will go for some specific type of column. So this lecture we are mainly covering the axially loaded short column. So we will see what are the guidelines given in the code book for axially loaded short column. Okay. So for that purpose we have to go to the code book, clause number 39, limit state collapse compression. Okay. So here it is given the minimum eccentricity in clause number 39.2. What is said? All members in compression shall be designed for the minimum eccentricity in accordance with the clause number 25.4. Where calculated eccentricity is larger, the minimum eccentricity should be ignored. Okay. We'll go to the next page and we'll see what is written. Okay, basically we have to see the clause number 39.3. Clause number 39.3 discuss about the axially loaded short columns. Axially loaded short column. So how do we know short column? If the slenderness ratio is less than 12. Okay, so axially loaded short column. Okay, what is said? The member shall be designed by considering the assumption given in so clause and the minimum eccentricity. When the minimum eccentricity is prescribed earlier does not exceed 0.5% of the lateral dimension. So whatever be the minimum eccentricity we have calculated earlier, 0, you can see earlier that Ex minimum or even Ey minimum we have calculated. What it is said that when the minimum eccentricity does not exceed 0.05 times the lateral dimension, in this direction say the dimension is dx, or in this direction say the dimension is dy. When in a column this minimum eccentricity does not exceed 5% of the lateral dimension, then we can design this column as a axially loaded short column. First of all, we have to see that their slenderness ratio is less than 12 in both direction. Then we have to see the eccentricity. The eccentricity is not exceeding this value, or you can say less than or equal to 0.05 dx. Okay, or less than or equal to 0.05, not exceeding dx or dy. In that case, we can go for design of axially loaded short column. Otherwise, we cannot. If these two conditions are not met, we cannot go for design of axially loaded short column. Let us assume that now what we are doing, we are trying to do the problem for axially loaded short column design. So let us assume that it is satisfying that slenderness ratio less than 12 and Ex and E minimum are less than or equal to 5% of the respective dimension. Then we can design axially loaded short column, and using the code book's guideline. What is that guideline? It said that Pu is equal to 0.4 FCK AC plus 0.67 FY ASC 0.4 FCK AC, it is not clear here, 0.4 FCK AC plus 0.67 FY AC. Now there is a new term. This FCK we know already, characteristic strength of the concrete. FY is known to us, yield stress of the steel. PU is the factored axial load on the column. Okay, whatever the load is given in limit state method, we take factor of safety as 1.5. So multiplied by this value. So factored, if it is working load is given, then you have to get the factored load multiplied by 1.5. ASC is the area of the compression reinforcement, longitudinal reinforcement. Okay, and then this AC is called the area of the concrete. What is area of the concrete? Now question is, area of the concrete, actually area of the concrete is equal to gross area of the section minus area of the reinforcement. Okay, say this is your column. In this column, this outer dimension if you take, that is called the gross area, and once you have provided the reinforcement here, then take this area of the reinforcement, this is called ASC. So difference between these two is called the concrete area. That means this equation we can modify, because initially we do not know what is the concrete area. So how to modify this equation? So we can write PU is equal to 0.4 FCK. AC means what? AG minus ASC plus 0.67 FY ASC. Now take the common term of ASC together. So what is this? 0.4 FCK AG plus 0.67 FY minus 0.4 FCK ASC. So this could be the equation finally. Okay, PU equal to 0.4 FCK AG plus 0.67 FY minus 0.4 FCK ASC. Here AG is the gross area. Okay, so this is what is the condition. So this we can apply in case of tied member. When helical reinforcements are provided, or we can say the spiral column is provided, in that case it is saying that, so what is given? This is given in clause number 39.4. Previous one was in clause number 39.3. Okay, so this one is given in clause number 39.4. What is said in clause number 39.4? Said compression members with helical reinforcement or the spiral reinforcement. It is said the strength of compression member with helical reinforcement satisfying the requirements of previous clause shall be taken as 1.05 times the strength of the similar member with lateral ties. That means what we have to do, we have to write down the equation in this case. In case of helical reinforcement, the equation will be 1.05 times 0.4 FCK AG plus 0.67 FY minus 0.4 FCK ASC. Okay, so in case of helical reinforcement, this equation will be modified like that. Okay, now another condition is given in case of helical reinforcement, that is given in clause number 39.4.1. The ratio of volume of helical reinforcement to the volume of the core shall not be less than this. The ratio of volume of helical reinforcement. Okay, so we have to find out that value, the ratio of volume of helical reinforcement. Let us say this rho T, I am writing like that, rho T or rho also you can write, is equal to ratio of volume of helical reinforcement per meter length. So I am assuming per meter length to the volume of core. So this is the ratio per meter length, let us say per meter length. So as per the codal provision that this shall not be less than means must be greater than or equal to, what is that? That is given 0.36 into AG by AC minus 1 then FCK by Fy. So this is a condition that is to be satisfied. Okay, when in case of helical reinforcement, we have to satisfy this condition. Okay, that volume of helical reinforcement to the volume of core shall not be less than 0.36 Ag by Ac minus 1 F into Fck by Fy. Ag by Ac, we know Ag is the gross area, Ac is the concrete area, not core area. Sorry. Here this Ac is indicating the core area. Okay, here Ac is indicating the core area, but earlier equation, if you go back, this Ac was something different, that was indicating the concrete area. So don't be confused. Here area of concrete, you can say CO. This could book is the same symbol, that's not good. CO is the concrete, and here this is talking about the volume of the core, area of the core. Okay, we'll discuss more in the problem. So this is the basic guidelines for axially loaded short columns. We'll quickly take an example and we'll see how we can apply all this whatever we have learned right now. Okay, rather than taking a simple problem, I will take a helically reinforced column, then it will be easy for you to apply on the other cases also. Okay, so I will take a helically reinforced. Okay, write down a question. Okay, the question is like that: design the reinforcement in a spiral column of 400 mm diameter subjected to a factored load of 1500 kilonewton. So the diameter of the column is given. Diameter of the column is given how much? 400 mm, and factored load Pu is given to us 1500 kilonewton. The column has an unsupported length of 3.4 meter. Unsupported length is given 3.4 meter and is braced against sideway. Condition is given that it is braced against sideway. Okay, it is given M25 concrete and Fe415 steel. I am reading again. Design the reinforcement in a spiral column of 400 mm diameter subjected to a factored load of 1500 kilonewton. The column has an unsupported length of 3.4 meter and is braced against sideway. Given M25 concrete and Fe415 steel. Okay, let us see how to do this problem. Okay, right now only one thing is known to us, that it is braced against sideway. That means what? That means this effective length ratio could be maximum of 1. It cannot be more than 1. So let us start. Let us start with the solution first. First, what we have to do? We have to check that whether it is a long column or short column. Okay, how to do that? So first find out slenderness ratio. Slenderness ratio is what? We know that L effective divided by lateral dimension. Here it is a circular column, so lateral dimension every direction is same. L effective is what? It is effective length ratio into unsupported length divided by D. Here we do not know what is the effective length ratio. Let us say it is K. What is L given? L is given 3.4 meter. So 3.4 meter if you write mm, then it is 3400. Divided by D is given how much? 400. So cancel. How much you are getting? This is giving you 8.5 K. Slenderness ratio is 8.5 K. Now there is a condition given in the question. It is said that the column is braced against sideway. When the column is braced against sideway, the value of 1 could be maximum 1. That is, it is ranging from 0.5 to 1. So that means if the K value is, even if we take that the K value is 1 also, so what will be this maximum value? This maximum value will be 8.5. So you can write down, since the column is braced against sideway, hence the maximum value of K could be 1. Therefore, maximum value of SR is equal to 8.5, which is less than 12. So we can say it is a short column. So therefore, it can be designed as a short column. Okay, now we know short column, still we do not know whether it is axially loaded or not. For that, what we have to do? We have to find out the minimum eccentricity. So minimum eccentricity, E minimum. In this case, it is a circular column, so E minimum will be same. That is equal to what? Unsupported length divided by 500 plus lateral dimension divided by 30 or 20 mm or 20 mm, whichever is minimum, right? Or whichever is maximum. Just go back and check the guidelines that I have written. If you see this, what I have written here, that whichever is larger, okay? So whichever is larger here we have to take. So what is this value? L is given how much here? 3400 divided by 500 plus D is how much? D is given here 400, right? Divided by 30. So if you do this calculation, this is coming how much? 20.1 mm. Okay. So or 20 mm. So which one is larger? Larger is 20.1 mm. So we will take this value as 20.1 mm. Now Cookbook said, what Cookbook said, that we can design as a accelerated short column when the minimum eccentricity does not exceed 5% of the lateral dimension. So what are the lateral dimension? Lateral dimension is 400. Okay, so we will go here. So we got E minimum is equal to 20.1 and it should not be more than 5% of D. So what is 5% of D? D how much? D was 400, so it is 20 mm. Okay, should not be less than this. Actually it should not be. Here 20.1 and here it is 20, so it cannot be an axially loaded short column, but since 20.1 is very close to 20, okay, so though it is not coming, but still we can say it is a axially loaded short column. Okay, and we can design it as a axially loaded short column. Okay, let us assume this, because it is very close 20.1, or otherwise if you want to change it, then we may need to increase this, decrease this L, rather than taking a 3400. Say if I change this in this problem itself, okay, let us say this is 3.2. If I take this value as 3.2, what will happen? Here it will be 32, so this value will be how much? 8. Okay, let us cut it here. This is 8, so in this value will be 8. So it is less than 12. This is fine. So if I take here 3.2, what will happen? This will be 3200. So 3200 by 500 plus 400 by 30. How much that comes? We can check. So if I change it like that, then this value comes 19.73. Then what will be the E minimum? Our E minimum will be 20, because out of this whichever is larger I have to take. E minimum will be 20. Then what I can say, that the E minimum should not be more than, that means less than equal to, because this is 20, so this 20 is less than equal to 20. Anyway, that doesn't matter, even if 0.1 or 0.2 is there, still we can say it is axially loaded short column. So ultimately what we can say, that we can design this problem as a axially loaded short column, axially loaded short column. Okay, so now we will apply the guidelines given for axially loaded short columns. Okay, so what are the guidelines available? First of all, what is given to us for axially loaded short column? Our equation is available. So what is given to us? It is given to us that Pu, what is the equation? Equation is Pu is equal to 1.05 into 0.4 FCK AG plus 0.67 FY minus 0.4 FCK AC, or otherwise we can write this 1500 kilonewton given is 1500 into 10 to the power 3 Newton divided by 1.05, 1.05, that is equal to 0.4 4 into FCK is how much given here in this problem? It is given 25 grade of concrete or what? 25 into gross area. Gross area is how much? Pi by 4 into d square, because column is given 400 diameter. Okay, plus 0.67. Fy is given 415, right? Yeah, plus, no, not plus, minus 0.4 into 25 into ASC. Okay, now you can do the calculation. If you calculate this as per the calculation given in this with me, the calculation with me is giving that ASC is equal to 642 mm square. Okay, so 642 mm square is coming the main reinforcement. Now you have to check that whether it is satisfying the minimum reinforcement criteria or not. Okay, so you calculate the percentage. This is 642 divided by gross area, pi by 4 into 400 square into 100%. How much it is coming? It is coming around 0.51%. So what is the guideline? Guideline said it should not be less than 0.8% of the gross area. That means we have to provide a minimum reinforcement. Okay, so we will provide ASC minimum. What is that? That is 0.8% of the gross area. Gross area is how much? Pi by 4 into 400 square. So this value comes out how much? 1005 mm square. So minimum we have to provide 1005 mm square reinforcement in this case. Okay, so now for, and also another guideline is say that we have to provide minimum 6 numbers of bars. So for 6 numbers of bar, what will be the diameter? So diameter you can calculate, say assume pi by 4 into diameter square into 6 number of bar is equal to 1005. Now if you calculate this, it will give you the approximate diameter, and I am getting an approximate diameter of 16 mm. Okay, because below that it is coming 14 point something, so it is to copy for 16 mm. So if we are providing 16 mm dia bar, then what is the exact reinforcement we are providing? So that means what we can say, that provide 6 numbers of 16 dia main reinforcement. So how much area we are giving? If you do the calculation, it is coming 1206 mm square. Okay, which is more than 1000.5. So this is okay. So main reinforcement whatever we have calculated is fine. Now we have to provide the spiral reinforcements. Okay, so to provide the spiral reinforcement, I need the core area, so I have to decide the clear cover. Let us assume, okay, write a heading, spiral reinforcement. First you assume the clear cover. Let us say clear cover, it was said that 40 mm or bar diameter whichever is larger. I am taking 40 mm. Okay, outside the spiral. Okay, that means what I am saying, that this is my concrete, and say this is the spiral boundary, then this is I am taking as 40 mm, and this is I am taking as how much? 40 mm. If my total is how much? 400. Okay, this outside is 40 mm, 40 mm. So what is the core diameter? Core diameter will be 400 minus 2 into 40, right? So I can write core dia equal to 400 minus 2 into 40. That is how much? That is equal to 320 mm, right? 320 mm is the core diameter. Okay, now we have to decide the pitch, decide the reinforcement diameter. What is the diameter guideline? That ST, if you just go back here itself, we have written there. What was those? Just little more. What was that? Tie diameter. Phi long max by 4 or 6 mm. Right? I have written phi long max by 4 or 6 mm, whichever is larger. It should be greater than or equal to. So phi long max by 4 we will see here. Phi long max greater than or equal to. 5 long max, what we are using? We are using 16 mm dia. By 4 is how much? 4 mm or 6 mm. So out of this, which one is maximum? 6 mm. So greater than or equal to, so I can take 6 mm or I can take more than that. This is not ST, this is phi t. I can take more than that also. Let us take 6 mm, that's not an issue. Okay. So we are starting with 6 mm itself. Okay. Now the condition is that this phi s or phi t or rho t, whatever, that is nothing but equal to volume of spiral reinforcement. So I am finding out volume of spiral reinforcement. I do not know what is the length, or forget about the length, per meter length divided by volume of core per meter length. Okay, so that has to be calculated. Now volume of spiral per meter length and volume of core diameter we know already. What is that? 320 mm. So what is the volume? It is basically a cylinder. It is basically a cylinder with diameter 320 and height I am taking as 1 meter. So what is the volume? Pi by 4 into diameter square into height. I am writing here height as 1 meter. Don't be confused. Okay. Now let us assume that for this spiral the spacing is ST. Okay. So if the spacing is ST, let me try to draw and try to explain you. Okay. Say this is the longitudinal bar and I am providing spiral reinforcement here. Spiral reinforcements are provided like that. Okay. Let us say the spacing of the spiral reinforcement is ST. Okay. And I am taking a total height from here to here is 1 meter. So my job is what? Volume of spiral per meter length I have to calculate. So how to calculate? So this spiral, what is the diameter? 6 mm. Right. So what is the area of the spiral? Pi by 4 into 6 square. This you will be agreed. Now next job is we have to multiply this by the length. Now how to calculate the length? Now see. Okay. If the spacing is ST and if I take 1 meter, say if I can say that this is approximately equal to some ring. Okay. This spiral, if I assume that this is the spiral reinforcement, approximately I am taking a circle. So this circle outside diameter is how much? 320, and here this width of this bar diameter is 6 mm. Okay, so what is the inside diameter? Inside diameter is 32 minus 2 into 6. So if I take the center point here, so what is the average diameter of this? Average diameter will be 320 minus 6. Right? So average diameter of the spiral is basically 320 minus 6. Now for one round, what is the length? Length is how much? Circle perimeter is how much? Pi d. So if I multiply it by pi d. So for one round, the area for one is this, how much? Pi by 4 c square. And for one round, what is this length? Length is pi into d. So I can write here multiplied by phi into 320 minus 6. Okay. So this is the volume for one round. Like that, how many rounds it is making for a 1 meter height? If you say the spacing is ST, then approximately it is making number of round is 1 meter divided by spacing. Okay, so this is the total number of round it is making. I am summary once again. This is the cross section area, and from here I got what is the perimeter of this. So one time round, what is the volume that we can calculate like that. So once I have the volume for one time round, then how many rings we are providing here? Approximately 1 meter divided by the spacing. So this is what. So this is the volume of spiral per meter length, and this is the volume of core per meter length. Okay. So what is the condition is given in the code book that this value should not be less than some specific value given. Okay, so wait. So this was how much? 4. As per the code book, this row S should be greater than or equal to 0.36 AC by A core. AC by A core minus 1 into FCK divided by FI. This is the conditions. Okay. See here whatever I have written, I can simplify it. Okay, you simplify this. That means if you simplify this, you will get the rho S like that. Rho S, okay, after simplification it is coming 0.3468 divided by ST. Now Coodle condition is that this value must be greater than or equal to this, or what I can say, that means 0.3468 divided by ST must be greater than or equal to 0.36. Okay, what is core area? Core area is pi by 4 into core diameter. What is the core diameter here? I have written, this is gross by core. What is the gross diameter? 4. So pi by 4 d square. What is the core diameter? Pi by 4 into 320 square. Okay, minus 1. What is FCK here? 25, and what is FY is given 415. Here pi by 4 get cancelled. So you can simplify this and you can find out the value of ST from this equation. Okay, you do the calculation part. It is giving that ST must be less than or equal to 28.4 mm as per this calculation. Okay, but as per the Coodle provision, what was the condition of ST? It was saying that ST must be less than 75 mm or core dia by 6. Core dia by 6. Our core dia is how much? 320 by 6. 320 by 6 is how much? 53.33. So the spacing must be less than 53.33, and also said the spacing must be greater than 25 mm or 35T. What was 5? 5 we have used here 6. So must be greater than 25 mm. Okay. What was the spacing we got by calculation? That it must be less than 28.4. That means we have to provide a center to center spacing or pitch, whatever we say, less than 28.4 but greater than 25. So I can take anything in between that. Let us say we are providing 28 mm. So finally what I can say that provide 6 mm dia spiral or helical reinforcement at the rate of 28 mm center to center pitch. Okay, and what was the main reinforcement we have provided? We have provided main reinforcement 6 number of 16 dia main reinforcement. Okay, you can draw and you can show it. This is the column. So outer of the column, so this is the outer of the column, and then main reinforcement 6 number 1, 2, 3, 4, 5, 6. So if you look at here, you cannot see all the 6. Okay, I can see 1, say center line I maybe see, maybe I can see say up to 3 here. Okay, then the spiral reinforcement, if you draw here, this is the how the spiral reinforcements. Okay, you can see here, you can draw here also, maybe something like that. Okay, so this is your design. Write down that what is this 6 number of 16 dia and what is this? It is 6 mm at the rate of 28 mm center to center. So, this is your design of spiral column. Okay, give the spacing whatever we have done. Okay, and you see that we have checked the minimum and maximum reinforcement also, and it was satisfying the criteria. Okay, so this is how you can design the column. You take some more examples. This one we have done for spiral. If you do it for lateral ties, also simple one, then don't multiply it by 1.05, and this checking is not required. Remaining part you can add. Okay, and then also check that whenever providing the longitudinal reinforcement, the center to center spacing of the longitudinal reinforcement should not be in any case more than 300. So, if it is more than 300, then provide additional reinforcement at the center. Okay. So, this is all about the design of compression member, basically axially loaded short column. Okay. So, we will see next topic in the next class. Till then, bye bye.